Discrete distribution. So we're looking at the kind of a mixture of the things we've done so far in this unit. It's essentially the last lesson before we get into the task later today, the review next class, and then the test following that. So we've looked at 3 types of distribution in this chapter. We looked at uniform, which is when the experiment's done once and there's an equal chance of each event occurring. For example, and this one's pretty popular, pretty common, rolling a single die, picking a card from a deck, maybe buying a lottery ticket. These are things where you always have an equal chance of each outcome happening. Then we looked at binomial distribution, when the experiment is done repeatedly with the same probability of success in each trial. So you're counting the number of successes that have occurred, and there was formulas that went along with that. And lastly, yesterday we looked at hypergeometric. The experiment is done repeatedly, but the probability of success changes after each trial, like selecting items from a distinct group, for example, committee questions. So, I'm going to ask you to identify which type of distribution is most appropriate to use in each one below. And of course, the best thing to do would be to read the question, pause it, and then answer, and come back and see if you got it right or not. If you're just watching and you're kind of just following along, I mean, it's not bad. It's better than not watching, of course, but it's not as good as pausing, trying, and then double checking. Okay, 6 marbles are taken from a bag containing 10 white marbles and 12 black marbles. What is the probability that 3 white marbles are chosen? Now again, remember, I'm not asking you to actually solve this probability question. I'm asking you to tell me which type of distribution would be most appropriate. Okay, so because you're looking at taking 6 marbles from a bag and you're not replacing them, this would be hypergeometric. Because the chances or the probabilities are going to change. As soon as you start taking marbles out and not replacing them, you're going to realize the probabilities are going to shift as there's less to choose from. Okay, next up. A single die is rolled 5 times. What is the probability that a 6 will appear on the up face in exactly 3 of those 5 rolls? Again, I'm not asking you to actually solve this question. We're going to just look at what type it is. So this one, because they are independent and you're repeating them, this is known as binomial distribution. Okay, because these are independent. In other words, if I roll a 6 and I pick up the die and I go to roll it again, I could just as easily roll a 6 as I could any other number on the face. Repeated trials. And the last one on this slide is 20 tickets numbered from 1 to 20 are placed into a hat. A ticket is randomly selected. What's the probability that the number 7 will be selected? So speaking of what we just talked about in the last slide, this would of course be uniform distribution because you're picking a single ticket. And really the big thing here, not only is it a single ticket you're picking, but that they're all equally likely. Okay, there's no one number or card that's more likely to get picked than another. Alright, let's do some actual questions where we're kind of mixing here the different styles. So make sure that it's really important to read these questions carefully and kind of figure out what they're actually asking us to do. For example, in a computer chip factory, 35 out of every 1,000 computer chips produced are defective. A batch of 20 chips is chosen at random. What's the probability that exactly 3 of these chips are defective? So first we're going to use this information given, this 35 out of every 1,000. And we're going to use that to determine our P, our probability of success. Okay, which is, 0.035 if I put that into a decimal. Now remember, if that's the probability of success, then the probability of failure has to be 1 minus that, because they have to add to 100%. Again, the most basic example I can give is if you're 50% chance of getting a heads, then you're 50% chance of getting tails. Okay, so we're going to take 1 minus this 0.035 and find out So that is 0.965. In other words, 96.5% of these chips are not defective. Alright, so the question said now we've got our P and Q. What's the probability that exactly 3 are defective? So what's the probability of X equaling 3? So we have 20 chips chosen, and we're going to choose exactly 3 of them, see if they're defective or not. And then we have P 0.035. Remember, to the power here, we're using our formula from the other day, power of 3, and 0.965, and remember it's 20 minus 3 to the power of 17. And we find out that it's pretty low. It is about 0.267. Now I'm pretty sure on the test I want you to use 4 decimals. I know I've been kind of like just round properly, but if the test is asking you for 4 decimals, I think it does, please try to follow that when you're writing that test on Monday. And it's good, just good habit to get into. Alright, what is the probability that at most one chip is defective? So here we're finding the probability of either X equal to 0 or X equaling to 1. So you can't have X2 or 3 or, so we're choosing this batch of 20. We only want 0 or 1. So we're going to find, remember that OR refers to addition, so we're going to find the probability of X equaling 0, and we're going to add it to the probability of X equaling 1. And so we're going to use the same, or similar, or the exact same formula. We're going to change, kind of massage the numbers here, because if we have 20 chips, and we're going to choose 0 in this case, that are defective, and we're going to multiply that by our 0.035 to the power of 0, and our 0.965 to the power of 20, plus, now we're choosing 1 to be defective. Again, same decimals. In this case, we have a power of 1 and a power of 19. Let's get rid of that. And we see, if we take our calculator, this is, again, the big thing you want to make sure you do on the test and even on the assignment later today, is to make sure you take your time and type these in. Even try it a second or third time just to make sure. 0.8461. Alright, question C. How many defective chips would you expect in the batch? Now there's that expectation. We talked about this many times. The expected is number of trials times the probability of that failure, in this case, the defective chip. So we are looking at 20 chips in this batch, and the P was 0.035. So we should say there's about, and it's pretty small actually, so there should be less than 1, right? Less than 1 chip should be defective, which makes sense. If there's only 35 out of 1,000, then if you're only picking 20, it should be quite a small number, or small chance of it happening, I suppose. All right. Let's move on. Example 2 here. A bin of fruit contains 4 apples and 8 oranges. 5 pieces of fruit are randomly chosen from the bin. So that 5 is important because it's going to talk about the number we're using as our first number in our kind of formula. So what's the probability that exactly 3, so we want 3 apples, is going to be, well, remember this is probability. Big difference from number of outcomes. Okay, probability always has to be a fraction. And I talked about this last week. If you like, and I do sometimes, I'm going to look at 4 apples and 8 oranges. So I actually have 12 pieces of fruit, and I'm choosing 5. I like to do my denominator first. That's my total out of number. You don't have to do that. I just like to. So let's go back to the question, exactly 3 apples. Well, there was 4, and we're going to choose 3 of them. There was 8 oranges, and now we're going to choose, now how many more pieces of fruit do we need? Well, if 3 of them are apples, then we need 2 more to be oranges in order to get that 5, that number 5. So it's approximately 0.1414. Okay, pretty straightforward, I think. Remember, watch the difference between number of outcomes and probabilities. What's the probability that all of the pieces of fruit are oranges? Okay, so now we're looking at x being equal to 5. Now remember, x here was apples, x here is oranges. Make sure you're clear of that. You don't have to change the wording at all, or the formula, or the way you write it. Just make sure you're aware of that. I personally like to put the top number here, the first number is the one I'm really looking for, and the second one's kind of what's left over. So all fruit are oranges. In other words, there was 8 oranges, and all 5 of them are going to be oranges. That means we still have those 4 apples, but in this case, we're actually not choosing any of them. And again, we have the same total number on the bottom. I've said this before, I'll say it again. First number should add up to the first number on the bottom. Second number should add up to the second number. Take your calculator, and it's 0.707. Okay, half the chance of the first one. All right, and the last one here. How many apples should you expect? There's that expected value again. So again, it's the same formula. It's EX. Now remember, we were taking 5 pieces of fruit randomly. And what were the chances of getting an apple? Well, let's go back. There was 12 pieces of fruit and 4 of them were apples. So really, your very most basic probability would be 4 to 12. So it's about 1.67. Therefore, between 1 and 2, maybe a little closer to 2 apples should be chosen that you should expect to get out of those 5. All right, let's continue on. You roll a single die and observe that the up face, in other words, the face that's facing up, as you would use if you were playing a game with the die. If you roll a 1 or a 6, you win $5. But if you roll a 2, 3, 4, or 5, you lose $2. Is this a fair game? Now, do you remember, and I hope you do, that for a game to be fair, the expected value should be 0. Well, let's find the expected value. So, if I roll a 1 or a 6, I'm going to win $5. So I'm going to win $5. And what's my probability of rolling a 1 or a 6? Well, there's 1 1 and there's 1 6, so there's 2, and there's 6 possible outcomes on a single die. Okay? Now, if I roll the rest of my numbers, I'm going to lose $2, so it's actually minus 2. And I have 2, 3, 4, 5, which is 4 numbers out of a possible 6. So I end up with 10 over 6 minus 8 over 6, which is 2 over 6, which is also 1/3. And therefore, if it's not 0, which it's not, this is not a fair game because the expected value doesn't equal 0. All right, let's think. If there's one last question we can do together before we start the practice homework, worksheet, whatever you want to call it. Example, a school lottery has 5,000 tickets for sale. There is 1 grand prize of $2,000 and 5 second prizes of $100. Okay, so kind of getting some numbers here already, crunching some numbers. Determine the expected value of the lottery and then explain what it means. So, again, expected value is going to equal, now in this case, kind of like the last one with the dice, $2,000. I'm going to win $2,000, but I only have there's only 1 grand prize, and there's 5,000 tickets. So that's my chance of getting that 1 grand prize. Plus, I also have this $100 prize, and this one there's 5 of them, so there's 5 prizes out of 5,000. It's a lot of tickets, 5,000. So I grab my calculator here. I'm going to multiply these fractions. I'm going to add them up. I'm going to end up with 0.5. Now I know this is a money question, so I'm not going to leave my answer, as 0.5. I'm going to say, therefore, that's 50 cents per ticket is the expected value. Okay, so again, I'm taking my answer. I know it's a money question, so I'm converting it into the proper form, I guess. How can the school use the expected value to help them determine the ticket price? Well, remember, expected value means it's fair. In other words, 50 cents, okay, this would mean that the school, they would break even. If they were to sell these tickets for 50 cents each. And you could take that a number of ways. You could say, well then, let's make some profit. Let's sell them for $1 each. Or maybe you look at it like, let's sell them for $5 each, but let's put a few more prizes in there. All right, all kinds of things you could do with this. But essentially, this expected value is saying what they're going to make on each one. So in order to break even, they would have to sell them for that. If they want to make money, they have to sell them for more. I don't think they want to lose money, so they wouldn't sell them for any less. Alright, so the handout, pretty quick lesson. The handout today is called More Probability Distributions Practice, and I am going to post the solutions for those if I haven't already. You can check them out, and then the second half of today's class is going to be the task for this chapter. Remember, tomorrow is review, and our test is Monday. Second last test is on Monday.